In this video, we will discuss about Venturimeter. See, Venturimeter is a device which is used to measure the discharge of liquid through a pipe. So in the figure you can see a pipe. This is the pipe, and in this pipe a Venturimeter is attached in order to measure the discharge or rate of flow in this pipe. Okay. So, as I told you, it is a device used for measuring the rate of flow of fluid flowing through a pipe. This is the figure, and this works based on Bernoulli's principle, and it has three parts. The converging part, where the area, cross-sectional area is reduced. Then you have a throat, where the cross-sectional area remains constant, and then you have a diverging part where the area increases and the original value is obtained. So this is a Venturimeter, and you can see that a manometer is connected, a differential manometer is connected at the inlet and at the throat. So section 1 is taken at the inlet and section 2 is taken at the throat. So in this figure, a differential manometer is connected, and the level difference between the liquid manometric fluid is noted, and that will be used for finding the discharge. Okay. So we'll see the expression of discharge in Venturimeter. This is the expression for discharge. Q actual is equal to CD into A1 A2 by root of A1 square minus A2 square into root 2 GH, where A1 is the area of cross section at section 1. I told you that section 1 is taken at the inlet. So A1 is the area of the pipe at the inlet. So it will be equal to the area of the pipe itself. Then A2 is the area at the throat. You know that at throat you have a reduced area. So you have to find out what is the area of cross section at the throat, and that will be your A2. Okay. CD is coefficient of Venturimeter, and the value of CD will be less than 1. It will vary depending upon the device. And you have a term H. In the figure, you can see that two piezometers are connected at section 1 and section 2. What do you mean by a piezometer? Piezometer is nothing but a transparent glass tube. So this transparent glass tube is connected to the pipe at section 1. So what will happen? The fluid is flowing with the pressure, and based on the pressure, the liquid will be entering the glass pipe, and it will be the water level, the liquid level will be rising. For example, in this figure, the liquid is up to this level inside the piezometer. Okay. So this height is measured, and this height is related to the pressure inside this pipe. Okay. Similarly, at throat also you can see that liquid level is increased inside the piezometer. Up to this level you have the liquid in the piezometer. So this height will give you the measure of pressure at this particular point, at 2. Okay. Now what is H? H is the level difference between the height of water or height of liquid in the piezometers connected at section 1 and connected at section 2. Okay. So H is in terms of the flowing fluid. The flowing fluid is entering the piezometer, isn't it? So this H is the level difference of the flowing fluid itself. Okay. So this is the expression. You need to memorize this expression to do problems. Okay. Now there are certain cases for finding H. In the first figure we saw that a manometer, a differential manometer. I'll show you the figure. This is the first figure. In this figure, a differential manometer is connected to the inlet and the throat. So in differential manometer, there will be another fluid, manometric fluid will be there. Okay. So you can see this dark colored fluid is the manometric fluid. But in the derivation, we are not using a differential manometer. We are using a piezometer. So another fluid is not there, only the water or the liquid flowing through the pipe is available. So H is in terms of that flowing fluid. But in most of the cases, we'll be using a differential manometer and we'll be getting the reading of the manometer in terms of another fluid, which is the manometric fluid. So, in questions, the reading will be given in terms of another fluid. But in equation, we have to use the reading in terms of the liquid which is flowing through the pipe. So, we need to convert that into H. So, for that, we have certain formula. So value of H, regarding value of H, we have different cases. Case 1, case 2. First two cases are applicable to venturimeter when it is horizontal. So in this figure, you can see that venturimeter is horizontal, and if you have the manometer connected and if the manometric reading is small x, see here, x is the difference of heavier liquid column in the U2 manometer. Okay, U2 manometer is connected, and in the manometer you will have a fluid, right? So in case 1, the manometer contains a liquid which is heavier than the liquid flowing through the pipe. That is case 1. So in case 1, you have to check two conditions. First condition is that the venturimeter is horizontal. Second condition is that the manometer contains a liquid which is heavier than the flowing fluid. Suppose I'll give you an example. Water is flowing through the pipe, and inside the manometer you have mercury. Which is heavier? Mercury is heavier than water. That means it is case 1. Okay, manometer contains a heavier fluid. So if that is the case, you can use this equation, H is equal to x into SH by SO minus 1. This equation can be used to find out H value. In the question, x will be given and you can find out H using this expression. Okay, what is SH? SH is the specific gravity of the heavier fluid. Heavier fluid will be in the manometer. So in the example that I gave you, mercury is in the manometer. So SH will be the specific gravity of mercury. Then SO is the specific gravity of the flowing liquid. So inside the pipe, some liquid will be flowing. Say water will be flowing. So SO is the specific gravity of water. So using this expression, you can find out H. Also, in a horizontal manometer, we can use this expression for finding H. If sometimes in some cases, the pressure at inlet and pressure at throat will be given. So in such cases, you can find out H using this expression. Here Z term will not be there because Z is the height of the points from a particular datum. Here the points are at the same level. It is horizontal. So Z term will not be there, only P terms will be there. Okay, so this equation can also be used in this case. Now we'll move on to the second case. In second case also, the venturimeter is horizontal, but the fluid inside the manometer is lighter than the flowing fluid. So I'll give you an example. Suppose you have water inside the manometer and through the pipe you have oil, coconut oil. Okay, we know that coconut oil, inside the manometer the liquid should be lighter. That means inside the manometer, say we have coconut oil and water is flowing through the pipe. Okay, so which is lighter? Oil which is inside the manometer is lighter. So that is case 2. Here it is written, manometer contains a liquid which is lighter than the flowing fluid. So in that case, we can use this equation. H is equal to x into 1 minus SL by SO. SO, as in previous case, it is the specific gravity of the flowing fluid, or it is the specific gravity of the fluid which is inside the pipe, main pipe, and SL is the specific gravity of fluid inside the manometer. Okay, and here also you can use this equation because the venturimeter is horizontal. So these are case 1 and case 2. As I told you previously, H is the head in terms of the flowing fluid, whereas X is in terms of the manometric fluid. In the equation, we should be substituting the value of H. But in most of the questions, X will be given. We have to find out H in order to find out Q. Okay. Now we'll discuss the other cases. In case 3 and case 4, the venturimeter is not horizontal. It is inclined. Okay, so in the figure, you can see an inclined venturimeter and a vertical venturimeter. In both the cases, Z values will be there. In the figure, you can see that Z1 and Z2 are marked. In the previous case, Z1 was equal to Z2. So, Z terms were not there in the equations. But here, Z terms will be there. Okay, so case 3. In case 3, the venturimeter will not be horizontal. It will be either inclined or vertical like this. So in that case, if the manometer contains a heavier liquid, then H can be found out using two formula. Just in the previous case, we have two formula for H. One equation is H is equal to P1 by rho G plus Z1 minus P2 by rho G plus Z2. That is one equation. Another equation is H is equal to X into SH by SO minus 1. This one was seen in the previous case also. Okay. So these two equations can be used in case 3. So in case 3, what are the 2 points that you have to consider? First one is that the venturimeter is not horizontal. It is either inclined or vertical. Second point is that the manometer contains a heavier liquid than the flowing fluid. So if these two conditions are satisfied, then it is case 3 and you can use these two equations. Then you have case 4. Can you guess what is case 4? Yes, in case 4, the venturimeter will be inclined or vertical and the differential manometer will contain a lighter fluid than the flowing fluid. See here, for inclined venturimeter in which differential manometer contains a liquid which is lighter than the liquid flowing through the pipe. In such case, it is named as case 4. For this case also, we have two equations for H. This is the first equation. It is similar to this one, and H is equal to X into 1 minus SL by S naught. So these two equations can be used for case 4. If you are thorough with these 4 cases, you can easily do all the problems related to venturimeter, and along with these equations you can apply continuity equation, Bernoulli's equation, etc. to the problems. Okay, so we'll discuss a problem. A horizontal venturimeter with inlet and throat diameters 30 cm and 15 cm respectively is used to measure the flow of water. The reading of differential manometer connected to the inlet and throat is 20 centimeters of mercury. Determine the rate of flow. Take CD is equal to 0.98. Okay. In this question, the given data are the inlet diameter is given, throat diameter is given. So from this diameters, you can find out the inlet area and throat area. Inlet area can be taken as A1 and throat area can be taken as A2. So here A1, area at inlet A1 is found out, area at throat is also found out. Then CD is also given, CD is equal to 0.98. Then the reading of differential manometer connected to the inlet and throat is 20 centimeter of mercury. So this pressure head is given in terms of mercury. What is mercury? Is it the flowing fluid or the manometric fluid? It is clearly mentioned that in the pipe there is flow of water. So the water through the pipe is, the fluid through the pipe is water, and the manometric fluid is mercury, and the reading is given in terms of the manometric fluid. That means this 20 centimeter is your X value. So reading of differential manometer, X is equal to 20 centimeter of mercury. Okay, but in the discharge equation we have H. H is in terms of the flowing fluid, so we need to convert X into H. For that, we can use this equation as the manometric fluid is heavier than the flowing fluid. In manometer we have mercury. What is the specific gravity of mercury? 13.6. In the pipe you have water. Specific gravity of water is 1. So which is heavier? Manometric fluid is heavier. That means this is case 1. Horizontal venturimeter and manometric fluid heavier than the flowing fluid. So this is case 1. You can use the equations of case 1. So this is the equation of case 1. Substitute the values and you will be getting the value of H as 252 centimeters of water. Okay. So see now H is in terms of the flowing fluid, that is water. Now this is the equation for discharge. CD is given, all the values are known. One point to be noted is that here we are substituting everything in centimeter square. So this G value, acceleration due to gravity, should also be substituted in centimeter per second. So 981 is substituted over here. Okay. So we will be getting the value as these many centimeter cube per second, and this can be converted into liters per second, and this many liters per second. Okay, so this is how you do the problem of horizontal venturimeter. Another question: a horizontal venturimeter with inlet diameter 20 cm and throat diameter 10 cm is used to measure the flow of oil of specific gravity 0.8. So what is flowing through the pipe? We have to measure the flow of oil. So oil is flowing through the pipe and the specific gravity of oil is 0.8. The discharge of oil through venturimeter is 60 liters per second. Oh, discharge is already given. Q is already given in the question. Find the reading of the oil mercury differential manometer. We just have to find the reading of differential manometer. Q is given. We have to find the reading of differential manometer. Okay, so we'll first write down the given data. Here diameters of inlet and throat are given. So A1, A2 can be found out. CD is given. Discharge Q is also given. Now we have the equation of discharge, and here the only unknown is H. Isn't it? All of the values are given. So substitute all the values and find the value of H. So we know that H will be in terms of the flowing fluid. Here the flowing fluid is oil. So H is equal to 289.98 centimeter of oil. But this will not be the reading of the manometer, because in manometer we have mercury. So we have to find out what is X. So for that you can use this equation. Here which is the case? Is it case 1 or case 2? Here the oil is flowing through the pipe and the specific gravity of oil is 8. In the manometer you have mercury. So mercury is heavier than oil. So in the manometer you have heavier fluid. That means it is case 1. You can use the expression for case 1. In this equation all the values are known except for X. So you can easily find out X value, and X is equal to 18.12 centimeter. This is the reading of the oil mercury differential manometer. Okay, this is the reading. So this is another type of problem. Then next problem: a horizontal venturimeter with inlet diameter 20 cm and throat diameter 10 cm is used to measure the flow of water. So what is inside the pipe? Water is flowing through the pipe. The pressure at inlet is 17.658 Newton per centimeter square, and the vacuum pressure at the throat is 30 centimeter of mercury. Yeah, here inlet pressure P1 is directly given. It is not, head is not given, pressure is self is given. You can identify that from the units. See here, if the unit is Newton per centimeter square or Newton per meter square, something like that, then it is the pressure itself. So this can be taken as P1. But look at the pressure at throat. It is given in centimeters. That means it is not the pressure. This is the pressure head. Pressure is P and pressure head is P by rho G. So this 30 centimeter of mercury is P by rho G. And one more point is to be noted over here. That is, it is vacuum pressure at the throat. In the previous modules, we have studied that this vacuum pressure is always negative. It is measured below the atmospheric pressure. So vacuum pressure is always negative. Wherever you see vacuum pressure, you have to take that value as negative. Okay. So pressures are given. Then you have to find out the discharge of water through Venturimeter. Take CD values also given. So we'll first write down the given data. Diameter, inlet and throat is given. So A1, A2 can be found out. As I told you, the pressure at inlet is given. So P1 is equal to 17.658 Newton per centimeter square. Converting that into Newton per meter square by multiplying with 10 raised to 4. So you got the P1 value, and this 30 centimeter of mercury, it is not the pressure, but this is the pressure head. Pressure head is P by rho g. So at throat it is section 2. So we have this equation for finding Q, and this H value need to be found out. This is a horizontal venturimeter. We can use this equation for H. See, we have two equations for H, isn't it? But for using the other equation, we need the value of X, the reading of manometer. But the reading of manometer is not given in this question. So you can use this equation for finding H. Now P1 is given. Then for P2, we need to find out H. This is the equation of H. P1 value is given. So we need to find out P1 by rho g. P1 by rho g is found out, and it is obtained as 18 meters of mercury. Now we need P2 by rho g. P2 by rho g is directly given in the question, but it is a vacuum pressure. So minus P2 by rho g is equal to minus 30 centimeter of mercury. Here P1 by rho g is in terms of water, but P2 by rho g is in terms of mercury. That is not possible. We need to convert this mercury to water. So what we do is we multiply with the specific gravity of mercury in order to get the pressure head in terms of water. So when you multiply with the specific gravity of mercury 13.6, you will be getting P2 by rho g as minus 4.08 meters of water. So P1 by rho g is obtained, P2 by rho g is obtained. Substitute the values in this equation in order to find H. So differential head H is equal to P1 by rho g minus P2 by rho g, and you'll be getting the value of H as 2208 centimeters of water. So this value, H value, can be substituted in this equation, and Q value can be found out. So substituting the value, here everything is substituted in centimeters. So Q value is obtained as 165.55 liters per second. Okay, so this is another type of problem. Now the next problem. This question is already asked in the university question paper. Find the discharge of water flowing through a pipe 30 cm diameter placed in an inclined position where a venturimeter is inserted having a throat diameter of 15 cm. So here you have a pipe, and inside the pipe you have water flowing, and the diameter of the pipe is 30 cm. It is placed in an inclined position. That means the venturimeter will be inserted inside the pipe, and the venturimeter also will be inclined. So this is case 4 or case 3. I don't know which case, but it is not case 1 or case 2. It is inclined venturimeter, so case 3 or case 4. Okay. Now it is having a throat diameter of 15. So A1, A2 can be found out. The difference of pressure between main and the throat is measured by a liquid of specific gravity 0.6 is in an inverted U-tube, which gives a reading of 30 cm. So here the pressure difference between the inlet and throat is measured using a liquid of specific gravity 0.6. So the manometric fluid is a liquid of specific gravity 0.6. Okay, so in the pipe you have water, and inside the manometer you have a liquid of specific gravity 0.6. Which is heavier? Water is heavier. So in this case, in the manometer you have a lighter fluid than the flowing fluid. So that means this is case 4. The venturimeter is inclined and manometric fluid is lighter than the flowing fluid. So this is case 4. Okay, and the manometer gives a reading of 30 centimeters. So this 30 is your X value. Then loss of head between the main and throat is 0.2 times the kinetic head of the pipe. Yeah, here you need to consider the head loss also. So when water is moving from the inlet section to the throat, there is some loss occurring. Okay, total energy are not same, some loss is occurring. So that loss is 0.2 times the kinetic head of the pipe. What is the equation for kinetic head? It is v square by 2g, where v is the velocity. So 0.2 into v square by 2g will be your head loss HL. Okay. Now we'll write the given data. Yeah, this is the figure. As I told you, we have oil is inside the manometer and water is flowing through the pipe. Here X value is given as 30 centimeter. Now inlet diameter and throat diameters are given. A1, A2 can be found out and X value is also given. As we have identified, this is case 4 and you can use this equation for finding H. And also this equation can also be used. You can refer the previous slides for the equations. Better you note down the cases to your notebook and then compare. Now here we can substitute the values and we can find the value of H. H value, X value is given, so H value can be found out and the H is obtained as 12 centimeter of water. Water is the flowing fluid, isn't it? Okay, now we know that head loss HL is equal to 0.2 into kinetic head of the pipe. That means 0.2 into V1 square by 2g, where V1 is the velocity at the inlet. Now we are applying Bernoulli's equation at section 1 and 2. At section 1, we know that in Bernoulli's equation there are three terms: the pressure head, the datum head and the kinetic head. So at section 1, we have P1 by rho g plus Z1 plus V1 square by 2g is equal to, at the second section at throat, we have P2 by rho g plus Z2 plus V2 square by 2g plus HL. There is a loss. So that loss should also be included in the Bernoulli's equation. Now we know that, yeah, here we are rearranging the terms and will be getting this equation. In this equation, P1 by rho g plus Z1 minus P2 by rho g plus Z2, this can be substituted as H value. See, these two are same. So these terms can be substituted by H. And what is HL? HL is 0.2 into V1 square by 2g. So substituting these values, you will be getting this expression, and taking all terms to one side, you will be getting this equation. Now we are applying the continuity equation to section 1 and 2. As I told you, in Venturimeter, basically in inclined Venturimeter problems, along with the equations that we have studied in case 1, 2, 3, 4, we will be applying the Bernoulli's equation and continuity equation. Okay, so we have applied Bernoulli's equation and we got an expression and it has V1 and V2. Now we will be applying continuity equation. A1 V1 is equal to A2 V2, and we'll be applying the values of A1 and A2. We'll be getting an expression between V1 and V2. So on simplification, we get that V1 is equal to V2 by 4. So this value will be substituted in this equation. Okay. So when you substitute the value in that equation and simplify, you will be getting the value of V2. V2 is equal to 157.4 centimeter per second. Okay. So once you get the velocity at a particular section, the discharge can be found out using the equation Q is equal to area into velocity. So Q can be written as A2 into V2. Discharge Q is equal to A2 into V2. And the answer is 27.8 liters per second. Okay. So this is how you do this problem. Then next problem. A 30 centimeter by 15 centimeter Venturimeter is provided in a vertical pipe carrying oil of specific gravity 9, the flow being upwards. Yeah, here in this question, the venturimeter is vertical. So it can be either case 4 or case 3. Diameter, the inlet diameter and throat diameters are given. Then specific gravity of the oil flowing through the pipe is 0.9. The difference in elevation of throat section and the entrance section of the venturimeter is 30 centimeter. So that means the difference in elevation of throat section and entrance section of the venturimeter is 30 centimeters. So the difference is the difference of Z1 minus Z2 is 30 centimeter, and the differential U2 manometer shows a gauge deflection of 25 centimeters. So this is your X value. Calculate the discharge of oil, that means we have to find out Q, and also the pressure difference between the entrance section and throat section. So P1 minus P2 is to be found out. Take the coefficient of discharge as 0.98 and specific gravity of mercury as 13.6. So what is flowing through the pipe? We have a liquid or oil of specific gravity 0.9. In the manometer you have mercury and the specific gravity is 13.6. So the inside the manometer you have a heavier fluid. So this is case 3. Okay. Now this is the figure. So this is 30. Suppose you have a datum over here. Okay. See, we are considering a datum over here. So this value will be Z1 and this value will be Z2. Okay. So what is 30? This 30 can be written as Z2 minus Z1. Okay. Now the inlet diameter and throat diameters are given, so we can find out A1 and A2. As I told you from the figure, it is clear that Z2 minus Z1 is equal to 30 centimeter. Specific gravity of oil is 0.9. Specific gravity of mercury is written. X value is also given in the question. So these are the given data. Now this is case 3. So we can use this formula and this formula for finding for H. So H is equal to this formula. X value is given, so using this formula we can find out the H value. H value is equal to 352.77 centimeter of oil, because oil is the flowing fluid. Okay, so we can substitute the H value in this equation and it is found out to be, Q is found out to be 148.79 liters per second. So first part of the question is over. Now in the second part we need to find out the pressure difference P1 minus P2. For that we'll be using this equation. We already obtained H value as 352.77. So opening the brackets, just open the brackets and you'll be getting P1 by rho g minus P2 by rho g plus Z1 minus Z2 is equal to 352.77. So we already know the value of Z2 minus Z1, isn't it? So substituting this value in this equation. Here it is Z1 minus Z2. So when you substitute, it becomes minus 30. And you will be getting the value of P1 by rho g minus P2 by rho g is equal to 3.8277 meters of oil. Okay, so you got the pressure head difference. Now in order to get the pressure difference, take by rho g into the other side. So P1 minus P2 is equal to this value into rho g. Substitute the value of rho g. What is rho? Rho is the density of the fluid inside the pipe. We know that specific gravity of fluid inside the pipe is 0.9. So 0.9 into 1000 will give you the density. So 900 is the density and G is 9.81. So substituting the values and simplifying, you'll be getting the pressure difference as 3.3795 Newton per centimeter square. Okay, so this is how you do vertical venturimeter problems. Hope the topic venturimeter and the problems related to venturimeters are clear to you. Thank you.